Our next speaker is Mariam Ali Akbarpur, and she's going to talk about towards testing monotonicity of distributions over general posets.
Thank you. So today I'm going to talk about testing monotonicity of distributions over general poset. This is a joint work with Themis Skoliakis, John Peeble, Renee Dribenfield, and Anak Yatpignani. Let me start by problem definition. Suppose we are given a poset represented by a directed acyclic graph on n nodes, and we have a distribution Q on the nodes of this poset. We say distribution Q is monotone if for every edge uv, the probability of u is at most probability of v. So the goal of testing monotonicity is to design an algorithm that distinguishes monotone distributions. The tester here receives samples from distribution Q, and it also have full access to the poset G, and we want the tester to output accept if Q is a monotone distribution, and output reject if Q is epsilon far from any monotone distribution. And we want the whole thing to be true with probability 0.9. But why monotonicity? Monotonicity is a basic fundamental problem and is interesting in its own right, but it's also an important structural assumption that helps us to perform other tasks more efficiently. For example, entropy estimation can be done exponentially faster for monotone distributions. Also, testing monotonicity is an important building block for studying the shape of distribution, for example, in testing and learning K-models distributions. The goal here is to design efficient algorithm with optimal sample complexity, meaning use as few samples as possible. So to give you a little bit of context that what this sample complexity could be, I'm going to give you two naive results. There is an upper bound that you probably have seen in the previous talks that we can learn a distribution over a domain of size n using O of n samples. So after we learn the distribution, testing monotonicity is a matter of just computation. And also for many posets, there is a lower bound of a square root n, which can be derived by some birthday paradox type argument. So mostly we are looking for this interval of a square root n in n to find the optimal sample complexity. Prior to our work, there were several posets that have been considered. I'm not going to go through the details of all these results, but what I just want you to see in this slide is that the sample complexity heavily depends on the structure of the underlying poset. So let me give you a subset of results that we have in the paper. We gave an upper bound of n over log n for matching poset. The matching poset is exactly what you can see in this slide. It's a matching graph, and the edges are from bottom to top. With a series of reduction, we show an upper bound for general poset that the sample complexity depends on the maximum degree. So for low degree graph, this can beat the learning upper bound that we mentioned earlier. Also, we provide a series of lower bound. The first one is a lower bound of n over log n for matching poset. This is the first optimal bound for matching posets in terms of n. And we also give an almost linear lower bound for hypercubes. The lower bound for the hypercubes obtained by embedding the hard instance of the matching in some middle layer of the hypercube. For the rest of the talk, I'm going to focus on the proof sketch of the lower bound for the matching poset. So we introduced an important tool. We introduced a new property as an important tool to prove our lower bound. It's called a T-bigness property. We say distribution Q is T-big for some threshold parameter T if all the probabilities according to Q are at least T. So what we do is we show a lower bound reduction from T-bigness property to testing monotonicity. So suppose I want to test bigness of distribution Q. I take a matching of the size n, which is the domain of the size of the domain of Q. I put the probabilities according to distribution Q on the top, and put T on the bottom, according to the picture. So after I normalize these quantities, what I would get is a distribution over the matching. And it's easy to see that Q would be, P would be monotone if and only if Q is a T-big distribution. So this reduction implies that if I achieve any lower bound for T-bigness property, it immediately gives me a lower bound for matching, monotonicity of the matching. So in the next step, I'm going to show a lower bound of n over log n for matching posets. So let's just review what a matching poset would potentially do. So if we start with some T-big distribution, here is Q plus, and draw samples from the Q plus and give those samples to the tester, we expect the tester to accept with high probability. On the other hand, if you start off with a distribution that is far from being T-big, then we expect the tester to reject with high probability. So what I want to achieve is two randomized processes to generate Q pluses and Q minuses, such that the sample set that they are generating are indistinguishable if I draw too few samples. So I just mentioned that the tester must definitely distinguish these two cases, which immediately gives me a lower bound for my tester. So what does this randomized process I just mentioned look like? In this randomized process, we're going to receive a prior distribution. You can think of it as a set of parameters that I'm going to later talk about it, how we achieve these parameters. And then we also want to generate a distribution over a domain of size n. So the way that we generate Q is as follows. We draw n random variable from distribution P, the prior. Let's call them x1 through xn. The probability of the ith element according to the Q is xi after normalization. And then after I build Q, I can draw samples from it and output those samples. What we need is to have two prior distributions, P plus and P minuses, which one of them generates T-big distribution, the other one generates epsilon far from T-big distribution such that their sample sets are indistinguishable. So what we do, we formulate the properties that we need for P plus and P minuses into an LP such that the solution of the LP would be exactly the P plus and P minuses. And if we solve the LP, then we get the desired lower bound that we want. So what we showed is that the LP that we just talked about is equivalent to an LP in the paper of the Wu Yang. And they show, using Chebyshev polynomials, that their LP has solution, which implies that our LP has a solution, and it immediately gives our lower bound results. So let me conclude by giving you an open problem. So currently, we don't have an upper bound for general posets with high degrees. So is it possible to come up with a sublinear algorithm that can solve this problem? And if there is no such algorithm, can we come up with a poset that actually requires omega of n samples? So that's it. Thank you.
Any questions?
I actually haven't thought about it, but that's an interesting question. So you're saying if there is some underlying structure in the distribution, then is this problem easier? I would assume yes, but I haven't thought about it.
Okay, thank you. Yeah. Next talk is on testing mixtures of discrete distributions by Mariam.
So in this talk, I'm going to talk about testing mixtures of distributions. This is a joint work with Ravi Kumar and Ronit Rubenfeld. So suppose we have access to samples from the queries that a web search engine would receive over the course of a year, years. And an interesting question might be, is the distribution that these queries are coming from are the same or they are different? But every month must be different than any other month. So maybe a more interesting question might be if these two distributions are slightly different versus substantially different. So a more formal definition of this problem is that we want to design an algorithm called tester that has access to distribution P and Q. This access might be through samples or explicitly knowing the distributions. And with probability 0.9, we want to output except if P and Q are almost the same and reject if they are far from each other. So what would be this almost closeness even mean? So one suggestion is to consider the L1 distance between the two distributions. This problem has been considered before, and it's called tolerant testing. So we have two threshold parameter epsilon1 and epsilon2. We want to distinguish the cases that L1 distance is smaller than epsilon1 versus the case that the L1 distance is larger than epsilon2. This problem is known to be notoriously expensive, and it requires n over log n samples to test. To just give you a little bit of context, if we want to test P is equal to Q when both of P and Q are accessible through samples versus the case that they are far from each other, this problem can be solved in O of n to the 2/3. So just by changing epsilon1 to 0, then this problem suddenly gets a lot easier. But let me give you a little bit of detail about how this lower bound could work. So we start with distribution Q. We perform like epsilon1 perturbation in the probability mass of the distribution and get another distribution. So the goal is to distinguish this resulting distribution with a class of far distributions. And it turns out, since the adversary can control both of these perturbation and far distribution, it's very hard for us to test. So one potential suggestion to get around this lower bound might be to come up with another model which is more restricted and give less power to the adversary. What we consider as an alternative model is the mixing with noise model. So we start off with distribution Q and we mix it with some noise and get a noisy version of Q. What we want to test is if P is the noisy version of Q or is it far from any noisy version of Q. So, but is this problem really less expensive than what I just explained? It turns out that there is still a distribution Q equal to uniform distribution, and adversary get to pick the noise distribution. And this set of noisy Q are indistinguishable from epsilon far from Q distributions, and it still requires O of n over log n samples. So this is still hard, even though that we kind of make our model more restricted. So it seems like as long as I give the adversary this power to kind of pick the noise arbitrarily, it's hard for me to get any upper bound. So what we do here is to essentially let the algorithm to have more information about the underlying noise distribution. So still I want to test the mixture testing problem. I want to see if P is a mixture of Q and noise. Here I'm going to call it R. Or is it far from any mixture? So we consider three cases. One is that the case that the noise is explicitly known. The other one is that the noise is available through samples. And the other one is that the noise is known to be in a class without any extra assumption. So let me give you the results we have. So in the first case, so we want to test P is a mixture of Q and R. P is available through samples. Q and R both are explicitly known. And what we get is a sample complexity of t to the square root n, and it's optimal. And surprisingly, this is the same number of sample you would need even if there was no noise in the model. So even if I was testing if P is equal to Q, I would need the same number of samples. Also, in another result, for the case where P we have sample access to, and Q1 are also available through samples, we get a result of a square root n plus n to the 2/3. These are two incomparable terms depending on what epsilon is, but in any regime for epsilon, we get the optimal result. And again, this is the same as what we would need in the case that there were no noise. And you might wonder what will happen if one of the Q1R was explicitly known and the other one was the sample. It turns out that all these combination is as hard as this problem, so that's also covered. There is another case that we consider where R is in a class of noise distribution. So P is available through sample, Q is explicitly known, and R, the class of, and R is in the class we consider is a class of K-flat distribution. So what is a K-flat distribution? It is a distribution that its probability mass function looks like a K-histogram. So the result that we achieve is an upper bound of a square root K times N. It turns out the lower bound for testing K-histogram is essentially a lower bound for our problem as well for the case where Q is equal to uniform. But essentially, this is the lower bound for our problem, which has a square root N plus the third root of K times N. So for the rest of this talk, let me focus on the proof sketch for the last result. So as I mentioned in this last result, we know exactly what Q is. It means that we know the probability of every single element according to Q. So what we can do is to partition the domain elements according to Q such that within each set of the partition, the probability of QIs are very close to each other. So this, in each bucket, the distribution sounds like an almost uniform distribution. So let's take one of these set of partitions. And for now, for the sake of the next few slides, assume that I exactly know what are the intervals that the noise distributions are flat on. This is not, and we usually don't have this information, but just for now, assume that we have this information. So what I'm going to do, I'm going to partition my domain for another level. So I take the intersection of each of these sets that I have with each of the interval in the segmentation I get. Still, it turns out in each new sets that I'm receiving, it must be, the distribution Q must be uniform on them, and it's also, since it's within one interval of the noise, then the noise is also a uniform distribution over that particular set. So even after mixing, I would expect to get some uniform distribution for all these new sets. So now, to see if P is a mixture of Q and R, what I do is that I look at each of these sets that I just explained and see if they are almost uniform. And then after I make sure that all of them are uniform, I learn the distribution over all these sets and check the overall shape of the distribution. P sounds like a mixture. And that's actually enough for testing if P is a mixture or not. But the main issue is that this segmentation is not known in advance. So what we do is essentially try all possible segmentation and use union bound to get the optimal results. So union bound helped me to reuse the samples. So it gives me the right sample complexity, but in terms of time complexity, this is very inefficient. So what we did, use some dynamic programming technique to make our algorithm efficient and avoid trying all possible segmentation. So I will conclude with open problems. So as you saw in the results part, our results were not tight for the last result. An open problem could be how can we fix that? And another open problem is that what other class of noise can we consider? And that's it.
We'll take one question from the audience.
Yeah, actually, if epsilon 1 is like, let's say 1 over poly n, I believe 1 over the third root of n, there is, you can retrieve a square root n bound. So it's the problem when epsilon 1 is almost a constant.